Hello and welcome to topic 3A. Let's put an A here, where we are learning, acquiring the knowledge, if you will, for our next topic. Now, what have we done in the past couple of topics? Mainly, we have been trying to describe data that comes from measuring one variable. Maybe I'm measuring the height of people. Weight, maybe something else. I get a variable, single variable, and I'm trying to calculate some measures to represent the collection of scores that I collected, to represent my data. In this next topic, we are going to look at what we call bivariate descriptive statistics. Ooh, such a scary word. All we're doing is investigating the relationship, or rather describing the relationship between two variables. The investigation will feature topic. So we're trying to essentially do the same thing, describing the data. But when we have two variables that are potentially somehow related to each other, we'll see things get a little bit more complicated in terms of how do we describe that and how do we describe it effectively. But we can still have a frequency table. Let's take an example. Just a random example here. I know there's a lot of numbers immediately, and my slides aren't the best. I had to write them out. I didn't have pre-typed slides, but I think it's good enough to get the point across. Let's suppose we have two variables. One is gender for kids at a school, and the other is whether they are in, or which grade they're in, rather. Grade 2 and 3, to keep things simple. Each variable will only have two possible values. Bivariate. Well, no, bivariate means two variables. Uh, but to keep things simple, we're going to, for the most of this discussion, have variables that only have two possible values. Dichotomous, they call it. But this can be extended to more. That's not really effective for our introduction. So we have this situation. Now, I just made up some numbers. Let's suppose there are 12 boys in grade 2. There are 10 boys in grade 3. There are 12 girls in, excuse me, whew, you got all choked up there. These 2x2 frequency tables are so pretty. So here, let me make a color. Let's pick a color. Well, maybe purple. Just purple. So here's my original four numbers. And because I have two variables, they sort of have overlap in different ways. There are 12 girls in grade 2, 16 girls in grade 3, and those are our numbers. So now the frequency table, if you will, have more options in terms of relative frequency. Yes, I can calculate the total number of boys, total number of girls, but I can also calculate the total number of students in grade 2, total number of students in grade 3. So I have different totals, and I can calculate relative frequencies, whether it's the fraction or the percentage, by way of the sort of the rows or the columns. Let's pick another color here. Let's make it a blue. So for example, I could say here, this guy, by looking at the grade 2 column, 12 out of 24 were boys. So 50% were boys. And therefore, of course, in grade 2, 50% were girls. But I can also go and look at the boys row and say out of the total 22 boys, 12 were in grade 2. I can calculate that very easily. I get, if I round it to one decimal place, 54%. So 54.5 rather percent of the boys in this data set were in grade 2. And then of course the other side of it were from boys were in grade 3. Calculate 10 out of 22, I get 45.5%. And so you can calculate these others, and I'm going to leave it to you. That's not hard to do. The point is that I have two ways of looking at the relative frequencies now, because I have two variables and they interact in a sense in different combinations. But still, I have my frequencies, if you will, my 2 by 2 frequency table. And we're going to stick with 2 by 2 for our introduction instead of making the options for the variables more. Okay, so it is a little bit more complicated looking because I have two variables and therefore two sets of percentages. Now, we don't necessarily want to look at all of the percentages. Some will have more meaning to us than others, but they are certainly all possible. Like I said, I could have larger dimensions of variables with more values. Nothing changes uh, in how I can set this up and present my frequencies, my relative frequencies, my percentages. It's just more of the same. So we'll stick with 2 by 2 now. If I want to do this, I could also use numeric variables with ranges, range groups. Let's say we want uh, have a few columns for the different scores they could get in a test. I might not want to have too many columns. I could break it up into uh, 0 to 25%, and then the next 25% in the test scores they could get. So I could certainly break a numeric variable up into a few categories by 2. And what we're trying to really investigate, uh, so take a first step to investigate, is a pair of variables that have a potential causal connection. What I mean is, in some way, we don't know how one might affect the other. And that comes in very often if we're trying to investigate if people are exposed to some risk, for example, lung cancer potentially causing, sorry, smoking potentially causing lung cancer, or I have a treatment that I want to administer and we're trying to see if the treatment has a positive effect. So the treatment, some sort of medication perhaps, causes an improvement in some illness. So that's mainly going to be our focus. So what we have, let me just hide some stuff here. What we have is, for consistency and convenience, we're going to pick the risk factor, like smoking is a risk for lung cancer, or the treatment in some other cases. We're going to put that variable uh, on the left side to form the rows. The values of the variable will form the row. The risk factor in some cases, treatment in another. So when I think of risk factor, I like to think of a specific example rather than just in general trying to memorize these things. If I think about smoking, the person could be exposed to smoking by smoking or not exposed. Values for this variable. Or if I think about a treatment, I can also think about it in terms of exposed or not. You're exposed to the risk of not getting the treatment. and you are not exposed to the risk by receiving the treatment. You might intuitively think, well, I could be exposed to the treatment and not. Absolutely. Just for consistency, uh, books that you might read, the nursing book, for example, that we reference, try and have some consistency throughout the setup from one problem to the next. Otherwise, it might be confusing for no real reason. And then the other variable will be our outcome variable that we're trying to assess if the risk factor slash treatment has an effect and what kind of an effect and how severe an effect on the outcome. If I think about smoking as the risk factor, I think about the outcome as being diagnosed with lung cancer, for example. And that outcome is yes, it's a positive diagnosis, or no, it's not. Or if I receive a treatment, then the outcome could be uh, testing for some illness. I either have it or I don't. Okay, so I have my risk factor making up the rows and my outcome making up the columns. You don't have to, but I find that if you keep flipping them around and shuffling where things go in my table, it just adds confusion for no benefit whatsoever. So, like I said, an example could be risk factor lung cancer, smoking. I keep switching them. Risk factor is obviously smoking, and that may directly cause lung cancer, or there just might be some connection to lung cancer. We can't, with this investigation, say, yes, smoking causes lung cancer because the numbers say so. No. All we can really say, or I'm trying to say, is there is a connection that smoking, directly or indirectly, increases your risk of lung cancer. But that's still a valuable thing to say and to know. Or you could think of, if I sort of stick to the same theme, a nicotine patch maybe, and you want to investigate that. Some people will get a nicotine patch, some people will not. It doesn't matter which row I put where, really. The numbers are all going to be the same, and relatively speaking, the information will be the same. And the nicotine patch might cause, or not, might cause, might not cause, but I want to investigate a connection between wearing a nicotine patch and still smoking after a while, or measuring the urge for smoking, or some measurement of the smoking outcome, yes or no. And then I can say, yes, there is a connection. Improvement. I'm hoping for an improvement, of course. Desire to smoke or the smoking habit. But it might not, in a necessarily direct way, cause less smoking. But there's still a relationship between these two that I'm ultimately trying to investigate. So hopefully that gets you the idea. Let's pick a specific example and delve into some detail. Let's look at this, and I've just picked the example that is in the nursing statistics and data analysis for nursing research book that we referenced in our very first video. Just for consistency, there's no point in jumping between too many different examples and getting confused. Build one and really see how we are going to say things. So let's look at the relationship potentially of marital status versus the possibility of getting postpartum depression after giving birth. So some information was collected, 100 women, and this the fictitious results, right? So under marital status, some of them were not married, 19 were not married, and 81 were married. Among the not married, some were diagnosed with postpartum depression, some were not. Under the married group, some were still diagnosed with postpartum depression, and some were not. right? Because things are not that simple. You could be married or not married and still have this outcome. We're trying to investigate, does does being not married or married increase your chances based on this data, increase your chances of potentially suffering postpartum depression. So now the percentages can serve, just like before, the relative frequency, the percentages, serve as estimates to the underlying probabilities. We don't know what is the probability of getting postpartum depression if you are not married. We don't truly know that because it's a very complicated uh, thing with lots of factors that potentially affect it, right? Situational and timing and all kinds of things. It's a very complicated variable in truth. But when we collect some data and we say, oh, from the not married people, 8 out of 19 had postpartum depression. That 8 over 19 can serve as a hopefully good guess for what the true probability is. We don't have anything else to go on. We have to take it as the probability, knowing that it's just an estimate. And if our people, our sample that we're measuring, getting these numbers from, is diverse enough and selected in a random appropriate way to be representative of the larger group that we're investigating, our percentages that we calculate will be fairly close to the true underlying probabilities, but it's the best we can do. So that concept of using our information to estimate true probabilities is really behind the scenes in one way or another. So that's all we can do. So now, before I show that, now we want to calculate some numbers to represent the situation. Just like before, we calculated the mean to represent what is happening to this data set. But now with two variables, it's a little bit more complicated, and there are different options of what we can calculate, all trying to say something about this by way of a single number, but they're not all the same, and there are pros and cons to all of them. So I just have more options for what I can calculate. And as we go through them, we will talk about the pros and cons for each. First one we want to calculate, and I'll just reveal it so we don't get confused and see too much, is the absolute risk. So now I'm thinking of the marital status as the risk factor, like not being married puts you at risk potentially for a higher chance of postpartum depression. That's what we're trying to investigate. So the absolute risk is our row percentage, just like we calculated before, of the outcome. So we'll say the absolute risk of not being married. Yeah, sorry, let me rephrase that. The absolute risk of having postpartum depression while not being married, the risk exposed group, I'm exposed to the risk by not being married, is 8 out of 19. You can see it as a decimal. You can see it as a percentage. Those are equivalent. Doesn't matter. So 42, I like percentages because they're specifically there to present numbers, to present ratios, to present proportions and fractions. So why not? 42%, just over 42%, the absolute risk. That makes sense from the numbers here. It's the straightforward relative frequency from the row. From the row, I see 8 out of a possible 19 that were not married had postpartum depression. So the absolute risk is then essentially my probability estimate of being in that risk factor group and having a positive outcome. So I can then, of course, do the same for the married group, the non-exposed group. So the absolute risk, postpartum depression in the married group is, of course, 12 out of 81, and that gets me 14.8%. Now, clearly, just from this, it should be quite obvious, assuming we can safely take these percentages as accurate estimates for the underlying probabilities, which we always will do. It's much more likely to get postpartum depression being not married versus getting postpartum depression being married. Right? So from this, the data suggests that you are more at risk if you are not married. Wrote that down a little bit, just a reminder, percentages serve as approximations for the actual probabilities. And we have to interpret this. So, right, the whole point of this statistical measure, trying to use a single number to represent what's happening, is to tell me something about what's happening. So the data suggests the married status is linked to a reduced chance of postpartum depression, or the not married status is linked somehow, not directly perhaps, but there is a link that being not married and married have different chances of postpartum depression. So I can say it in terms of the married status being linked to a reduced chance, or the unmarried status being linked to a higher chance of postpartum depression. So there's nothing wrong with this. It gets the point across. It's great. But we can potentially say a little bit more. Like, yes, okay, it's better. Being married seems to result directly or indirectly to a lower chance of postpartum depression. We can now mix things up, and we have options to say how much better is it. We want to present the data in as convenient a way as possible. Just giving people two percentages and leaving it up to them, some might be okay with that. Some can look at these numbers and see, oh, okay, roughly 3 times as bad to get postpartum depression if you're not married versus married. But not everyone, right? They want to be uh, given everything. They just want the number. Don't ask me as the reader to do any sort of calculation. So we want to also present a number that tells me exactly how much better is or how much worse are my chances of getting postpartum depression being unmarried versus married. We want to calculate that for the reader. And that is called the relative risk. Calculate that. All it is, if I have my two numbers here, 42% and 42.1 and 14.8, how much more is one from the other? Well, that's just a simple division, right? So I'll calculate my relative risk. It keeps bumping my page up. I don't want to show that much. I'll calculate my relative risk of postpartum depression between unmarried and married status. As simply, you can take the percentages, you can take the decimal versions, it's going to be the same thing. Remember, I might write here a rounded version, but when I do the calculation, which we'll see in the upcoming videos, make sure you use the most accurate numbers, right? And I get 2.842. That's decimal. I can then convert that to a percentage as well. However, the percentage in this case is a little bit more difficult for people to wrap their heads around. So let's just not worry about that just yet. I'll come back to it in a second. 2.8 times. Here, this is, why am I writing in blue? Well, why not? 2.8 times worse to be unmarried versus married. And of course, I want to interpret that. So let's do it. You are almost 3 times more likely to have postpartum depression if you are not married. So, yes, you didn't need to calculate that. Figure it out from these percentages, absolutely. It's just another number you can present to really drive it home and say, ooh, 42% versus 14.8%, that is almost 3 times, so not that slide, 3 times a higher chance of having postpartum depression if you're unmarried versus married. Another number we can calculate is the absolute risk reduction, the difference between the two percentages. Now, addition and subtraction with percentages, it's not common, but in this case, an alternative is to see the difference between the two percentages, in this case 27.3, and then we can interpret that, I'll show it all, the extra proportion of people who would be harmed from the risk exposure. So if I look back, where's my slide? That one. Look at the table here and the percentages. Like if I just investigate postpartum depression being affected by marital status, whether you are not married or married, is not going to allow you to avoid postpartum depression completely, right? So not married is worse, but even if you're married, there's a 14.8% chance. There's always a chance. On top of that, there's a 27 point, what was it? 27.3 chance. In addition to sort of the baseline risk that you would be exposed to anyway in terms of marital status. So in addition to the quote unquote normal 14.8% chance, because there's still a chance, you're not avoiding this completely, there's a 27%-ish chance. Or 27% of the people on top of the normal 14.8 is at risk by not being married. So what is confusing here in general is that we have so many different numbers to essentially say the same thing. They're all built. They're all calculations using those original percentages, right? It's just different options to convey essentially the same thing, but really make it as clear for the reader if you're writing this report, to make it as clear as possible. And you have different options. No single one of them is the one you have to use always. It's just options. And because of those options of what numbers you can present, what numbers you can use to present your findings, there is some subjectivity. It's up to the author to pick some of these. You don't want to just throw all of them at the reader. That could be confusing too. Because on the at face value, they are different numbers, right? But they're all trying to say the same thing. So it becomes a little bit of a subjective issue to know what to present to really convey the information as effectively as possible. So absolute risk reduction is another option. We can then go a little further and do what we call relative risk reduction, where we'll take that difference, but of course, a 27% difference only really makes sense if I place it in the context of the original percentages, and we'll use the smallest one because it'll make the number just easier to interpret. The smallest one that I'm at risk of postpartum depression is 14.8, right? So 27.3 might seem like a lot, but if I had a sort of baseline probability of over 50%, well, then 27% is not as much as if I had a baseline risk of 14.8%. So all the absolute numbers don't convey the full picture. The relative versions are definitely better. So relative to that quote unquote baseline married probability, the 27.3% over my original base 14.8 is 1.842. Now, if I compare that to the relative risk of 2.842, you'll see it is 1 or 100% less. So what the relative risk reduction allows me to say is the actual increase, percentage increase on top of the base. So I like to think of this one in terms of percentage and interpret it as you are 184% more likely to have postpartum depression if you're not married, or your chances of having postpartum depression is increased. It's an increase of 184% if you're not married. So when I think of these numbers and I read them, I think about 42%. Okay, 42% is kind of high. 14.8%, none of them super scary. Postpartum depression is a real thing. Different numbers sort of have different level of impressiveness. And if I say that being not married is 184% higher probability, it's an increased probability of getting postpartum depression if you're not married. That sounds a little scary. That sounds a little scary. Or if I say your chances are almost three times more. Some people that sounds scary. But to the casual or somewhat casual reader, the impression that you get from reading you're three times more likely, or yeah, three times more likely to have postpartum depression if you're unmarried versus your chances of having postpartum depression is increased by 184% if you're not married. One of them, to you personally, would sound a little bit more impressive than another. And this is where the subjective aspect of presenting the information unfortunately comes in. That might be an author who wants to really make this sound as impressive as possible, not changing the numbers in any way. The numbers are not manipulated. Nothing done here is unethical. But presenting some of these numbers will sound a little bit more scary than others. And it depends on um, what your motivations are, what you're trying to do. If you're trying to really caution people against some sort of risk, then you want to say it in a way that sounds as impressive as possible. Or if you want to sell some new treatment, you can just say, oh, 42% and 14.8%, do with that information what you will. Or you can use the the relative risk reduction, because they sound much more impressive in a way, even though they are exactly the same information. It's coming from the table regardless. So it's important to be aware of how these measures, these statistics are perceived, even though it's the same information, just presented in different packages. Some sound or are perceived very differently, and that's just the reality because we are beings and we read things in different ways and have our own experiences that affect our perception and how we feel about these numbers. So, it's an important issue that we should be aware of. That's not even the end. We have more numbers to present the information in the same information, but a different package. One is very interesting. The number needed to treat could have some meaning to people. What is that? NNT for short. The number of people from the exposed group, unmarried in our case, to statistically select one outcome. That is, one person that has a positive outcome. So if I look at my table here, I know that even from the married group, there's a 14.8% chance of, if I select a random person from this 81, there's a 14.8% chance of getting someone with postpartum depression. That's just the probability of it. But if I select someone from the not married group, from this 19, there's a 42% chance. Now, if I see the marital status sort of as a treatment, I can avoid postpartum depression by treating, quote unquote, the people and having them get married, statistically speaking. But so then everyone would have a 14.8% chance. The difference, the 27.3 it was, 27.3% of these not married people could have been treated by way of marital status and avoid postpartum depression, statistically speaking. Now, I want to sort of catch one of those people. I can't just pick one. Chances are I won't get one. I need to pick a good number so that 27.3% of them will have postpartum depression, and I want at least one whole person. So let's think about this. So remember this difference, 27.3%. Those were the percentage, the proportion of people from the not married group that have postpartum depression in addition to what's normal in terms of being married. So the percentage means out of 100. So 27.3 people in every 100 get postpartum depression that could have been treated by way of this married risk factor. So it takes 100 people to get 27.3 positive, 27.3 postpartum depression positive cases. So how many people do I need to have to get one whole person that tests positive for postpartum depression? Well, if you know a little bit about ratio equations, not a blue line, I can set up a little ratio equation here as 100 correspond to 27.3, question mark corresponding to 1. I cross multiply, I get 3.663. So of course I want to round up because I need to take a whole person. So it takes 4 people selected randomly from the not married group, and I will have a person that has, statistically speaking, postpartum depression, but it could have been avoided. So that's a whole thing just to justify where this calculation comes from. You can see here it's always going to be 1 over the decimal version of the absolute risk reduction, the 27.3, or it's always going to be a 1. It's always going to be 100, divided by the percentage version of the absolute risk reduction. I like to work with percentages because they just feel nicer, but I do have a short calculation, 100 over ARR, to calculate the number needed to treat. But when I first looked at this, I didn't immediately understand, why is this the calculation? It makes no sense to me personally. So I wanted to give you a little bit of an explanation for where this 3.6 comes from. So to some people, it has value to think of these things in terms of number needed to treat. That how many people do I need to treat or consider to avoid one of these cases? And of course, the underlying probabilities affect that. If I need to treat hundreds of people to just get one and avoid one person for the outcome, then that's because the chances are very close together, that the risk isn't really increasing my chances. It's hard to get just one person above baseline. So the smaller this number, the more significant the gap, or the more impressive the gap between them. Uh, it'll come from whatever the previously calculated percentages are. But I can present this so that people don't have to do those calculations for themselves. They just want to read the results and make decisions based on that. Me as the author, I have to go and calculate these things. It's not the reader's responsibility necessarily. So I have a choice to present maybe a few of these, maybe just one. It's up to me. Whatever I think will really drive this point home most effectively. We are getting close to the end, but sadly that's not the end, because there is more ways of presenting this information. And this next one might be a little bit confusing. It is the odds ratio. Now, before I can really do that calculation, I have to understand technically what we mean by odds. Odds are used in a variety of ways when I just speak casually. But odds are defined in this setting as the ratio of the probability of one event to that of an alternative event. It is the ratio of probabilities. Let's look at a simple example. Let's suppose I have a bag that contains 2 blue marbles and 3 red marbles. The probability of choosing blue is obviously 2 in 5, right? Or 2 out of 5. 2 blue marbles out of a possible total of 5 marbles. So my chances of selecting one and getting that one marble to be blue is 2 out of 5. Simple probability, one that we see with a concept that we see often. So because of that repetition that I'm exposed to this concept of probability, it starts to feel more natural and not strange at all. Whereas odds might not be something I have experienced a lot, and therefore it feels a little bit strange if I think about my personal experience. But it's a different way of saying the same thing. If I take this choosing blue as the desired event, the odds of choosing blue is 2 to 3. Now the probability is still in here, but the odds are presenting it in a way, the ratio, remember, of how many ways can I get what I want versus how many ways can I get what I don't want. 2 to 3. 2 blue marbles versus 3 red marbles. If I add them together, then I get the 5 and I can calculate the probability, and there is of course a very strong link between the probability and the odds. But it's just presenting the same information in a different way. Not right or wrong, just different. I can then sort of standardize this odds expression by calculating the ratio of these two numbers that feature, in this case 2 and 3, as 2 divided by 3, and I get 0.67, and it's a way of standardizing the odds that answer to 1. So the answer of this ratio will always be to 1, and therefore I don't have to say the 1, and I can present the odds as 0.67. Right. Not as common, for me, definitely not. But understand that it is a different package, a different presentation of the exact same thing. The exact same thing. And I'll be able to get from one to the other, probability to odds, odds to probability, if I choose to. Okay. So now let's go to our postpartum depression example. The odds of having postpartum depression if not married, remember the table, 8 versus 11. No, this slide. 8 to 11. That those odds are presented as a decimal or a fraction, 8 divided by 11. Let me stress, that is not the probability. Decimal is simply because I want to present the odds as a single number, not this 2 to 3, 8 to 11. Standardized version of the odds. So the odds will be 8 to 11 or 0.727 to 1. Okay. The odds of having postpartum depression if married is then, of course, based on my table here, 12 to 69. Or presented as a single decimal number, 0.174. Of course, the odds are smaller because the odds are still connected very closely to the probability. They are not probabilities, technically speaking, not directly. The odds of having postpartum depression if married is 0.174. The probability is not, right? The probability was 14.8% or 0.148. They're close in some cases. They're not the same thing. They are, however, saying or referencing the same information. So in some cases, some people like odds, and again, what makes this complicated and confusing is I have so many different options to refer to the exact same data. Just unfortunate that can potentially create confusion. So then the odds ratio is simply the ratio of the odds. Very similar to relative risk, but using the odds instead of the probabilities. If I go back and look at the relative risk, these percentages are the probabilities of having postpartum depression between married and not married. And I simply put them into context by dividing the small one into the big one, and I get that my chances, my probability, I'll emphasize, my probability of having postpartum depression being unmarried is almost 3 times worse, almost 3 times more than my probability of having postpartum depression being married. It was a ratio of probabilities. The odds ratio is a ratio of odds. I take one odd divided by the other one, or the big divided by the small. I think for consistency might give me a more comparable number, and I get 4.182. Interpreting this is important. The odds of postpartum depression if not married, I guess are 4 times more, 4 times more than if you were married. Just like relative risk was the ratio of probabilities, ratio of percentages, the odds ratio is the ratio of odds, ratio of odds. So I just say here, there is a difference in the number itself, that the odds ratio say 4 times more. The relative risk says 3 times more. So because readers don't always understand odds versus probabilities and how they are linked but not the same, there is a real risk and a real danger for the reader to not interpret the results presented, not correctly interpret the odds ratio. And there is a debate between which one should be presented, which one should be used. Should we use both all the time? Should we just stick to one? Because if you, as the reader, are not as experienced working with odds and interpreting odds, you just see, oh, something is 4 times worse. I don't know what. I don't quite understand odds, but it's 4 times worse, so it must be bad. Versus being presented with, oh, it's 2.8 times worse. Oh, that's not so bad. I feel okay about that. Yet it's the same information. It's the same underlying information coming from these numbers. The numbers have never changed. The issue is, how do I present the information in a way that gives the reader the most accurate in picture of the situation in the most effective way. Before I say that, so there is a downside I'll talk about as we wrap up. I know this one has been a little bit longer, but there's a lot of things happening here. In the relative risk to odds ratio debate, I have to really be aware of it, especially when the effect of the risk is bigger. The odds ratio and the relative risk will not be close to each other. If the effect of being married and not married is very small on postpartum depression, then the relative risk and the odds ratio will be very close together, and it really doesn't matter. Like if one says, oh, it's 2.8 times worse, and the other one says it's 2.9 times worse, what does it matter? Really. There's no risk in sort of leading the reader astray. However, most of the time, we are trying to find something that has a significant effect. It's important that we, as that the author presents things in a way that is accurate. All of these things are accurate, but also gives the reader the appropriate information and the reaction. So, unfortunately, what happens is the researchers and authors take advantage of the fact that most readers don't really understand the odds ratio, and the odds ratio will be larger than the relative risk. So if I just look at the number without really understanding what's happening here, I see 4.1 times worse versus 2.8 times worse. If the author just presents the odds ratio, I might think it's my fault as the reader, but it's common that I might think that the situation is worse than it actually is because I don't truly understand odds ratio. Our experiences sort of guide us to how to perceive odds. If I think about it, if I think about it, how we speak casually. If I think about the rain, let's suppose, maybe I should write this down. Suppose the chance of rain, chance meaning probability, of it raining today is, say, 40%. Okay? Let's say there's a 40% chance of rain. We all have a pretty good understanding of what that means. But if I were to ask someone, what are the odds of it raining today? Most people, and you are welcome to try this, if I casually ask people that I run into, what's the odds of it raining today? 40%. And everyone would understand what that answer is and how that answer is appropriate. But that means that people intuitively, based on limited experience, but still, intuitively perceive odds as being the same as probability, which it's not in the technical sense. No one, well, unless you have prior experience, I think, no one is going to answer the question, oh, what are the odds of raining today? Oh, it's 4 to 6. No one's going to say that. You need prior experience with the actual definition of odds to have a good feeling for how to use this. Or then we would uh, say that as 4 divided by 6, so 0.67. No one would say it. Or if I reverse this and I say, the odds of it raining today is 0.67, how many people are going to interpret that as 67%? Incorrectly, but it's still the reality that we don't interpret odds correctly. So even though the author isn't being unethical and manipulating data by presenting an odds ratio of 4.182, the more important question, in my opinion, is should they present the odds ratio, knowing full well that there is a high chance of the reader not really understanding what this 4.182 represents, when they could present the relative risk, and there's a much higher chance of the reader understanding what this 2.842 means. But authors want to have the most impressive number to really sell their findings and convey how impressive it is. And the odds ratio will be most of the time bigger and therefore more impressive. Should it be used? That is an ongoing debate. But at the very least, we have to be aware of the issue. I'll wrap it up by noting that it's important to look at all the measures. I don't want to have a single measure as the be all and end all, and I don't necessarily want to present absolutely every measure I can or statistic, but this should be in context to a few. If I look at the relative risk, if it comes from the absolute risk, remember absolute risk just being the percentages. If it comes from an absolute risk exposed group, let's say has a 6% chance of having the outcome versus the not exposed group, 2% chance. My relative risk is 3. So I'm 3 times, we casually say 3 times as likely. Well, actually, that's true. I'm 3 times as likely to have the outcome if I'm exposed in the exposed group. However, in a different situation, I could have an absolute risk exposed group of 60% and not exposed is 20%. The relative risk is still 3. I'm still 3 times more at risk. So the relative risk on its own doesn't present the full it's not like it doesn't present the full picture. It is correct and it uses all the numbers, but it's only relative. The two percentages relative to each other. It's in the name, relative risk. When those original percentages might have been so small, the relative risk being 3 times or 3 isn't necessarily a terrible thing. Versus 60 to 20, that's a much bigger deal. That's a very big reduction of 40%, right? In terms of the difference between the two. So I should always look at these measures in a big picture way and not just see one and sort of jump to conclusions potentially. All right, hopefully that gives you a pretty good introduction to this topic of bivariate statistical measures when I have multiple variables and I'm trying to describe the link between them. We'll revisit this issue of establishing a connection between two variables and maybe describing a causal relationship, but we're going to leave that until later. Next up, we are going to work through some examples on this in a little bit more detail, emphasizing the concepts as well. Until then.